Okay, we're going to take a look at why aren't all volcanoes the same. So the first slide we're going to look at is flood basalt. These things can be absolutely massive. In fact, some are measured in millions of cubic kilometers. The result from mantle plumes, oh, I should also add in there, just by way of interest, that when these things erupt, they can actually begin their eruption and complete it several millions of years later. So these can be absolutely colossal. And in fact, the thinking now is that they may have contributed to some of the mass extinctions over the history of the Earth. So where does all this magma originate from? Well, it turns out it's mantle plumes. And mantle plumes, which are also known as hotspots, can be particularly large areas of magma inside of the mantle. And as it expands upwards and flows out over the surface, what you can possibly end up with are things like flood basalts. And so we're looking at an image here, and you can see that not only is it thick, but the areas can be incredibly broad. This basalt differs somewhat chemically than ocean floor, but that is beyond the scope of this course. Are these things explosive? No. Because they have low silicates, they also have low viscosity, and so it just flows nicely. While there might be some localized explosions because a little bit of the material that's ejected might get backed up a little bit, primarily what you would see here would flow quite nicely. Now, it would wreak havoc, of course, on the atmosphere because of the CO2 that's also emitted, and that's the sort of thing that would have contributed to mass extinctions. So let's just go back and take a look at this chart that we've talked about in class. And there are a few problems here. If we start on the right-hand side, if flood basalts are the most viscous or result from the flows of the most viscous lava, shouldn't they be ultramafic? Well, if you look at the chart, the top row of rocks, so where we see peridotite, that top row, peridotite, gabbro, diorite, and granite, are all phaneritic rocks. And because they're phaneritic, that tells us that they must be intrusive or plutonic. So we got a problem. This chart suggests that there are no ultramafic extrusive rocks. And in fact, that is the case. So let's move to the left. And if you remember, and for those who don't remember, there is a short video I made that explains how continents form. And I do cover things like fractional crystallization, dewatering, and partial melt in that video. So because of all of those factors, what happens is that magma that is ultramafic deep down inside the mantle, by the time it hits the surface, it's going to end up being mafic. And so partial melt again means that those minerals that have the lowest melting temperatures are the last to crystallize. And so as it cools, as it rises, the highest temperature crystallizing minerals, such as the dark ferromagnesian minerals, are going to solidify first, and some will actually separate out of the melt or fractionate out of the melt. And so what we end up with is every time we watch magma rise from deep down inside the earth, whether it's from the magma, or sorry, whether it's from the mantle, or whether it's from a subduction zone, by the time it gets to the surface, it's going to increase its felsic concentration. Aha! That's a bit of a key here. And so what happens is that ultramafic magma becomes mafic. And now what we see in that mafic column, which is the second column, is we see basalt. And that's how, or that's why, those ultramafic flows end up as mafic on the surface. All right. I don't know if I made that entirely clear, but what we can also see from this column, if we look at the color index, is we would expect these things to be fairly dark, and that is the case. They should have, if we look at the left-hand side of that column, around 40% or 45%, up to as high as 80% concentration of dark ferromagnesian minerals, which again suggests that these things are going to be very dark in color and also very dense. And also, actually, one more thing, they're also going to have a fairly low viscosity relative to the higher silicate columns, which are still on the left. So the source, where do these things come from? Well, as already mentioned, they come from hotspots. We can see a diagram here showing Hawaii. Now, that's a bit troubling, though, because the picture I showed is clearly not Hawaii. So what's going on here? Well, hotspots historically could potentially fuel flood basalts, but we haven't seen these for quite some time historically. Hawaii, on the other hand, is one that's actually happening right before our eyes. And so what we have is we've got a hotspot underneath an oceanic plate, And what has happened is it's found a way to exploit or melt its way through, and some of that magma is being released as lava on the surface and forming Hawaii. If we look at it in profile, we don't see plateaus forming, though. What we see is actually a shield volcano. Now, these also have low viscosity. If you had to pick one volcano to stand next to as it was erupting, this would probably be the best choice from a viscosity perspective, because you wouldn't have to worry about much in the way of explosions, and you'd be able to pretty much outrun or outwalk the flowing lava. I'm not suggesting you stand by the side of a volcano as it's erupting, but if I had to make a choice, this would be my first choice in terms of personal safety. So does that mean this is composed of basically the same material as what we saw in the first slide? The answer to that, for the purposes of this course, is yes. It's basalt. Okay, it originates from essentially the same place. The real difference for our course is that this happens to be over top of an ocean plate, and the flood basalts happen to be over top of a continental plate. All right, let's move up the ladder one more to the left. Okay, so one more column to the left into the intermediate zone, and what we see is a stratovolcano. This is Mount Rainier, just outside of Tacoma, and you can see this is a very, very tall structure. However, if we go back and we take a look at Mauna Kea, if we could measure this or add on to it the 6,000 meters that are below the surface of the water, we actually have a mountain that's considerably larger than even Mount Everest. So this is big, this is bigger. Anyway, what's happened here? Okay, well, first of all, the source of the magma is entirely different. This is not coming from a hot spot. The source here is a subduction zone. And along that subduction zone, eventually, the rock that is subducting eventually hits a high enough pressure that dewatering occurs. When the dewatering occurs, we have that's the beginning of the melt zone. What we see happening is the introduction of volatiles, and the gases, the water vapor, etc., that are released from the dewatering cause that rock, or assist that rock, to melt. And as soon as it melts, what we see is a decrease in density, and it's going to eventually force its way to the surface if it doesn't solidify first. So if enough of it melts, it's going to find its way to the surface and eventually form a volcano. So again, we have a different source, and remember that the oceanic plate that's subducting is going to be made of a mafic material. Okay, it's basalt. The continental crust, on the other hand, is going to be composed of intermediate to felsic material. And if we mix both of those together, let's assume that they roughly equally melt along that melt zone. What we're going to see happening is, rather than mafic material rising up, we're going to see primarily intermediate to felsic. So let's take a look at the intermediate zone. What we expect would be an increase in viscosity, because we're increasing the silica content. We would expect a lighter color. Look at the color index along the top. And we'd see that we're now seeing a decrease, not surprisingly, in the dark ferromagnesian minerals such as biotite, amphibole, pyroxene, and olivine. Diorite and andesite, of course, would be the rocks. Diorite being the intrusive, andesite being the extrusive rock that we'd most likely find. So if we had to pick up, or if we did pick up a rock on the top of Mount Rainier, and I told you to guess what it was without even looking at it, and you guessed andesite, you'd probably be close to right. It might be rhyolite, but a pretty good chance it'd be andesite. So we've worked our way to the left for all columns except for the last one, which is the felsic column. Now, there's a couple possibilities here. The first one we'll talk about is a lava dome, and that lava dome occurs as a result of a volcanic plug that builds up after an eruption. So this is Mount St. Helens. It erupted last in 1980. Okay, so we're going to go inside that crater, inside the crater that resulted from the explosion in 1980 at Mount St. Helens. And what we see growing there is a lava dome. So what exactly is this thing? Well, it's felsic material, and that felsic material, which is incredibly viscous, it forms in just about a perfect plug. You can see there is some venting occurring. There is material that will be released, and it will slowly build up. Some of it's being pushed up from down below and actually rising up. Sometimes these things result from a little bit of lava that comes out the top. But basically, this thing is a plug in the top of a volcano, particularly a recently erupted volcano. And its felsic material is going to result, again, from that rising magma. And it's the stuff that basically forms a cork. If we look on the color index, we'd expect it to be the lightest material. And if it were intrusive, we would expect it to be granite. Of course, this is not. It's extrusive. And so we go to the bottom column. And so we would expect that this would be rhyolite. All right. Last structure that we see is a caldera. And what is a caldera? I mean, sometimes these things are called a crater. In fact, this is Crater Lake, or at least that's his name, although this is certainly not a crater. Probably a sinkhole would be a better description for it. Now, what happened here was this was a stratovolcano. A stratovolcano erupted. The eruption was catastrophic. So rhyolite is the most likely rock. That's the rock with the highest viscosity. And so what would have probably happened was there was so much pressure underneath that when the magma chamber finally erupted, it blasted its contents out to the point where the magma chamber was essentially emptied. When that magma chamber emptied, the volcano no longer had the structural support to hold itself, and so the entire thing collapsed into the magma chamber. And what we end up with is what looks like a crater. So these can be some of the most explosive volcanoes, and again, not a surprise when we're dealing with felsic materials. Actually, even though this looks pretty big, this is relatively small in terms of calderas. And for a moment here, we should talk a bit about the Yellowstone caldera. The Yellowstone caldera, when it last erupted, it was over 1,000 cubic kilometers. Now, if we contrast that with Mount St. Helens, when it erupted, it was 1.3 cubic kilometers roughly. You can look the number up. But that means this was, I don't know what that is, 600-700 times, sorry, not this particular volcano, but if we look at the caldera in Yellowstone Park, it was 600 or 700 times the volume of material that was ejected compared to Mount St. Helens. Really, really quite extraordinary. Let's take a look at that chart again. And just to finish off, rhyolite or possibly granite. If it's felsic and intrusive, it'd be granite. If it's extrusive or volcanic, rhyolite is a rock that we would expect. All right, that's it.